Can you hear me? Okay. Thank you for having us. I would like to thank Racy Grant as well because that's the reason why we were invited. Today we're both coming from GEOD, which is a new institute that we recently created in order to combine geopolitics with classic network theory in order to have a holistic perception of what internet is. Um, so Today we are going to discuss about internet and especially how internet is a space, and as a space, different actors are going to exert influence over it. And in this presentation, we will try to introduce you to different methodology we came up with in order to have an understanding of how this influence can reshape internet and what are the bottlenecks we are confronted to when it comes to traffic engineering. Because internet is something that we would like to improve overall, especially in the Middle Eastern region, but we're often confronted to political issues. In order to do so, we will use BGP, which is a natural setting in order to do to answer those questions, because routing is, as you are aware, highly political. So this presentation will be decomposed into three different topics: the question of representation, topological versus geographical, and borderizing in cyberspace. My colleague will do the second half, and I will do the first half, which is more technical. So I guess I don't necessarily have to redefine BGP, but I will do, so we agree on where we stand currently. So BGP is, as you know, a policy-based routing protocol. It's relatively simple, yet very complicated to configure, because a single misconfiguration can have an impact on a global scale. And therefore, you need to come up with a way to understand this interaction between local to global scale. And it can become very tricky, because you understand what happens locally. But when you look at a bigger region, since you have local preferences that enter into account, you end up having something that is very intricate. So, as you're aware, BGP object can be represented using many ways. In RIPE, for example, you have what they call routing dumps, which are just tables of routers. We decided to infer AS level graph them from this. So AS level graph is basically a decomposition of the BGP graph into ASs, which are the autonomous systems. I guess you're probably aware of this since most of the people here owns as AS. So there are distinct regions of administrative control, usually managed by a single institution. This institution can be a service provider, a company, a university, and so on. We observed that usually there is a hierarchy in the autonomous system. You have what we call the tier 1 ASs, which corresponds to ASs who have a role to connect the nation to internet. And what is interesting to witness is that depending on the country, your tier 1 is going to be very different. And this is something we're going to see later on. Then you have the medium-sized regional provider, and then you have the small network, which are usually the users of internet. And those are the customers you want to route toward. The reason why we decided to go for BGP at first is in the last part of this slide, where we mentioned that internal topology is not necessarily shared between ASs, but you need to have a certain coordination in order for routing to function. And therefore, BGP is one of the rare places where the actor needs to be transparent to a certain extent, something they wouldn't necessarily do. Usually actors tend to, especially in geopolitical question, they tend to conceal information. But when it comes to routing, you need to have a certain trust, and you need to come up with a way to interact. So what we obtained from those BGP updates is something of this format. So we use BGP Stream, which is a tool that was provided by RIPE, and we get a lot of information. We usually get more than 500 messages per second, and then we collect them in a JSON format, where we see that we have the collector, which corresponds to which server localized this announcement, this BGP announcement. We have the message, whether it's an announce or something else, the peer, the fields, the prefix. but we're not necessarily interested in this data per se. So we will augment it in order for it to really satisfy what we're trying to look for, which is have a BGP connectivity graph in terms of AS. So we augment it, and then we append so the short path, which tells you which AS it has crossed throughout its journey, which country it has crossed as well in GeoPath, the names of those AS, the risk, which is an aggregated value we come up with, which tells you how risky this path was in terms of probability of a hijack. So this is something that was defined by Luxembourg University at the beginning, and we developed something that also takes into account geopolitical risk into it and tells you, well, this road is going through countries it usually doesn't go to, and this is a source of risk as well. And then finally, we have a few other information which are not necessarily very interesting. So now that we have come up with this whole thing, we can actually define our BGP graph, which tells you, well, my AS are going to be my nodes, and there is going to be an edge between two nodes in the case I see a link that connects two ASs through the prefixes. So a link can be inferred to be broken when all prefix passing by it are withdrawn. No more prefix, it means that there is no more way to go from this AS to this AS, and therefore we suppose that it's broken. This allows us to infer the AS topology, and we're going to update it throughout time with respect to those new dumps we receive. Constantly, we're going to update it so that we have the best perception. And this notion of best perception is something that is really relative. Usually what we experience is that when we try to mix several feeds, we have so when we have a BGP announcement coming from a certain node of our graph, we are going to have some BGP announcement that are going to be withdrawn and are going to be filtered. So we need to have as much as possible landmarks in order to have the best view possible. So we use around 25 landmarks because we realized that it was the best way. So after 1 hour, actually this is something we've improved since then, we end up having a almost complete graph, BGP graph. And this is what we end up having. So here we see that we have a graph where the US and the Canada are going to represent the wide majority of it. And then we have Western Europe, which is central because Western Europe is usually connected to every part of the world. So it's going to be the center of our graph. Then we see different localization that happens naturally. We see that, for example, there is not necessarily a correlation between how big a country is in terms of its geography and how many ASs it ends up having. So those are things that are quite interesting. And in order to really analyze those, we come up with a new model which allows us to know what is the influence one country has over another one. In order to do so, we use graph embedding. So the idea of graph embedding is something I'm not going to go too much in details. If anybody has a question about it, we can talk about this later because it's rather technical. But the idea is really to say, well, in my network, there is a similarity measure which quantifies how influence this part of the network is by another part. So for example, if I look at the BGP graph of Lebanon, and I want to know how influenced it is by the BGP graph of France, I'm going to look at the similarity measure, and I need to define the similarity measure. And in order to define the similarity measure, we use spectral embedding, and we end up having a graph like this one. I skipped the previous slide because it's rather technical, and I don't want to get lost in this. But this slide is very interesting. So we see that here, we represent the BGP graph, and we see some region naturally appearing. You have USA, which, as I said earlier, corresponds to the wide majority of the BGP graph. Then you have Iran, Ukraine, Russia, Brazil. You see that Iran is quite disconnected from the rest. You see the same about Russia and Ukraine. And then we do this spectral embedding in order to understand what are the main powerhouses, what are the different area of influence. And we see that the yellow part corresponds to the part that is under influence of the USA. And you see that's the vast majority of the internet that is under influence of the USA. Then you have the blue part, which corresponds to Brazil. Brazil is its island. It's an island on its own. Same about Iran, which ends up having its own color. And then Russia and Ukraine becomes one part of the connectivity. Sorry. My colleague is gonna go a little bit further into the details and explain how, in the case of Middle East, it can get really interesting to see. So I'm gonna give him the mic.